In this video, I'll show you how to solve the problems from Fourier transform. You know that Fourier transform is the most important and difficult topic in signals and systems. But I hope if you can go through this video till the end, you will be able to solve any problems from Fourier transform. Let us start. We'll start from the Fourier transform, the basic concept. We'll consider signal xt in time domain, and its Fourier transform we'll consider capital X of j omega, or sometimes it is written as capital X of omega, and it is defined as capital X of j omega equals to integral of x of t e to the power minus j omega t dt. This is called Fourier transform, and from this spectral, this x of j omega is spectral or frequency content of the signal. From that, we can get back the original signal x of t by taking inverse Fourier transform, and this is defined as 1 upon 2 pi and integral from minus infinity to plus infinity of x of j omega times e to the power j omega t with respect to omega. So we have discussed this Fourier transform, is basic concept in detail in my previous lectures. So if you have some doubt, you can go through those videos. You will get the fundamentals about Fourier transform. But in this video, we'll discuss how to solve the problems from these basic equations. Okay. First, we'll try to calculate few Fourier transforms or spectrals of certain signals. Especially these 5 signals I'll consider, and I'll try to find out its Fourier transform from the definition of Fourier transform only. The first one is the unit impulse signal. And you know, the unit impulse signal is defined in this way, that del of t is a symbol, del is a symbol for impulse signal, and del of t equals to 0 when t not equal to 0. So this function will exist at t equal to 0 only, and the integral of del t over entire range is equals to 1, and that is due to unit impulse. So area under the signal is 1. Okay, so you can understand that at t equal to 0 its amplitude is very high, and other than t equal to 0 its amplitude is 0, but total area under the signal is always 1. Now we try to compute the Fourier transform of del t signal using the definition of the Fourier transform. So del t, the Fourier transform is del t times e to the power minus j omega t dt. Now here we'll use this property that whenever we will multiply one signal xt with del t, we can derive it as it is x of 0 times again del t, because del t is present at t equal to 0 only, otherwise it is absent, its value is 0. So whenever it is 0, if you multiply something, it will remain 0. So the product will look like again del t. So at t equal to 0, its value is x of 0. So that will give you certain multiplication with del t. Okay, thus the shape will remain del t, and what its amplitude is modified by x of 0. So that I have done here. So del of t e to the power minus j omega t. So here we'll put t equal to 0, e to the power 0, and e to the power 0 equals to 1. And now you will get integration of del t dt, and its value is 1 because we have considered unit impulse signal. So it's implied that the unit impulse signal is having Fourier transform 1. So in graphically we'll show these things. This is the time domain representation. At t equal to 0, you are having one impulse here. We'll put on arrow. So this is your del of t, and its Fourier transform is constant 1. for all frequencies. It implies that it is having all the frequencies with equal magnitude. Okay. Next, we'll consider exponentially decaying signal. X of t equals to e to the power minus at ut. We can compute the Fourier transform of this signal from the definition only. Now you see, this Fourier transform of x of t is integration of x of t to the power minus j omega t dt by definition. Now we replace x of t by e to the power minus at times ut. Then as u of t is 1 for right hand side, t more than or equal to 0, other than 0, otherwise it is 0. Thus the limit we will consider is 0 to infinity, because minus infinity to 0, this u of t is 0. So if anything is multiplied by 0, it will vanish. So the limit we will consider from 0 onwards only, 0 to infinity, and that time ut is 1. I replace by 1. So this product is now e to the power minus at times e to the power minus j omega t dt. Now we can combine these two, right? So if I combine these two, then you will see this minus common, a plus j omega times t. So this integral, we can do that one, e to the power minus a plus j omega t dt, sorry, j omega t upon minus a plus j omega. This is the integral of this signal, e to the power mx. Integration of e to the power mx is e to the power mx upon m. That we have done. Now limit we will consider 0 to infinity. When this is infinity upon limit, so e to the power minus infinity will become 0. Right? We'll assume that a is positive. Right? If a is positive, then obviously it is exponentially decaying signal. Okay, and there is certain limit on this a. That is fine. So this is 0, and this one is minus, and this one will give you t for 0 equal to 1. So 1 upon a plus j omega. So minus 1 upon a plus j omega. So this minus and minus will make plus. So it is becoming 1 upon a plus j omega. Thus, we have obtained that for this exponentially decaying signal e to the power minus at ut, its Fourier transform is 1 upon a plus j omega. Okay, this is most important. We will be using this signal frequently. So you need to remember the Fourier transform of this signal. So x of omega, its magnitude now we can calculate. It is 1 upon a square plus omega square, that's square root. And its angle will be, so this angle is tan inverse omega upon a. As it is in denominator, numerator angle is 0. So 0 minus tan inverse omega upon a. That is your total angle contributed by this spectral. Now we can draw these two shapes. This is your magnitude plot, this is your phase plot. This is your signal, time domain exponentially decaying signal. At the left side it is 0. Okay, its Fourier transform will look like this. This is the magnitude plot, and you see this one, magnitude is decaying, because as omega is increasing, this magnitude is decreasing. It is showing like this. Okay, and highest amplitude will be at omega equal to 0. That time value is 1 upon a, this one. Okay, and the phase is approaching to 0 to minus 90 in positive side, and negative side it is 0 to plus 90 degree, because at omega equal to infinity, tan inverse infinity will become pi by 2. Okay, thus as positive infinity it will become minus pi by 2, at negative infinity it will become plus pi by 2. Okay, now we'll consider one important signal, that is called rectangular or window signal or gate signal. It is also called gate signal. So this is the shape. It's one window within minus t by 2 to plus t by 2. Its magnitude is 1. Otherwise it is 0. Okay. So it is symbol we will consider sometimes capital pi. So capital pi within t upon capital T. This is the notation. It shows that its center point is 0 and width is capital T. Center is 0 and with total width is capital T. Left side minus t by 2, right side plus t by 2. Okay, so this is mathematically it is defined as it is equals to 1 within the range t equals to minus t by 2 to plus t by 2. That we can write as mod t less than t by 2, or we can put equal sign as well, and it is 0 otherwise outside. We wish to compute the Fourier transform of this signal. It is important. So the Fourier transform we'll consider here. So it is by definition xt e to the power minus j omega t dt, its integral. Now x of t is 1 within this range, so we'll consider this range minus t by 2 to plus t by 2. That time x of t is 1, that's all. And outside its value is 0, so we'll ignore that range because that area will become 0 because x of t is becoming 0. Okay, we'll consider only this non-zero range minus t by 2 to plus t by 2. That time we replace x of t by 1. Okay, now we need to integrate this one. So integration is very simple. E to the power minus j omega t upon minus j omega. It is minus, limit is minus t by 2 to plus t by 2. So if we put these two, what we'll get? This 1 upon j omega is I'll take outside. So upper limit is plus t by 2. I'll put it here. So it is minus e to the power minus j omega t by 2. This minus sign is for this minus sign. Okay. Now again I should put minus, minus minus it will make plus. And now e to the power minus j omega minus t by 2. That will give you plus sign here. Plus j omega t by 2. Now if you rearrange these two, this one if I take first, so e to the power j omega t by 2 minus e to the power minus j omega t by 2, and we'll consider 2j here. So j is already there, that j I'll take here, and 2 extra 2 will multiply here. So again we need to multiply 2 here. Okay, and this omega is already there. So this form e to the power j theta minus e to the power minus j theta upon 2j, it will give you sine theta. So that we'll use. So this is your sine of omega capital T by 2. So it is 2 upon omega times sine of omega t by 2. Now this is the rectangular or window signal in time domain, and its Fourier transform we can sketch. So this is the function x omega is 2 upon omega sine of omega times capital T upon 2. So we can plot this one. So we can rearrange this function as, so we can multiply t both numerator and denominator, and we can consider 2 here. Then it is sine omega t upon 2. This is becoming again omega t upon 2, but t is also there. With this t cancel out, and this 2 upon omega we have considered here omega upon 2. Okay, this form sine omega t by 2 and omega t by 2 sine x by x form. Okay, we can take limit. We can understand at omega equal to 0 what is the value. So at omega equal to 0, this is 0 by 0 form because sine of 0 is 0. This is also 0. So we need to take on limiting case. So here t is outside and sine x by x is limit x equal to 0 is 1. So that I will put it here. So it is t times 1 equals to capital T. So at t equal to 0, its value is capital T. Okay, that we have understood. Now this function 2 upon omega, this will, we can consider this one as one envelope. So I have discussed these forms, okay, these complicated forms in detail in my previous lectures. You can go through that one. So 2 upon omega, whenever it is multiplied with sine functions or cos functions, so this function, other function which is multiplied, it will give you some envelope, because when sine function or cos function will fluctuate within 1 and minus 1. So when it will become 1, it will touch to this upper envelope, and when it will become minus 1, it will touch to the negative envelope. Okay, so 2 upon omega is a positive envelope, this one. As omega is increasing, this value is decreasing, rectangular hyperbola. Similarly, this one as well. So this first quadrant and third quadrant, this is for 2 upon omega. Now negative envelope we can consider minus 2 upon omega is this one, is fourth quadrant, as well as here. Okay, now this signal x of omega should be bounded within these four walls, and it will start from this capital T. Okay, so it should fluctuate and it should touch these two envelopes. Okay, so you see this is the figure. So this is your function, and this function is commonly called as sinc function. So if we have rectangular time domain signal, the spectral is a sinc function. This is a very common signal. We'll be using this signal frequently. Okay, you need to remember this is expression. So pi t upon capital T, its spectral is 2 upon omega times sine omega capital T by 2. Okay, we'll use it. So now I'll show you one more important thing. So if I consider this width is small, then this is the shape, because it will cross this one sine omega capital T by 2. So sine function will become 0 when it is sine of pi, 2 pi, 3 pi, like that, sine k pi. Okay, so first cos point 0 will be when sine of pi means sine omega capital T by 2 equals to pi, means omega equals to 2 pi upon capital T. Okay, this is the first cos point. Next point is 4 pi upon capital T, like that. Okay, now you see if t is small, this width is small, then this point is very large, far away from this point, right? And if t is large, then this point will come closer to the origin. I'll show you this one. Now we have increased this width. So you see this point is coming very close. It is fluctuating more frequently. And if it is increased further, so it will look like this. So you can understand that when xt is now becoming 1, it is constant for all time. So this window, this capital T is becoming infinite ideally, capital T. Then you will get one DC signal, xt equal to 1, xt equal to 1. And we can understand that this magnitude, you see this is the capital T. As capital T is going towards infinity, this amplitude is becoming infinite and this width is becoming 0. So it is close to impulse signal. So when DC is your input signal, this signal in time domain, its spectral means its frequency domain representation is impulse. Okay, so that we can get. So we'll show you that x of t equal to 1 for this DC, its Fourier transform is exactly 2 pi times del omega. Okay, this is our next task. So our next task is to understand this signal x equal to 1, and we wish to compute its Fourier transform. Now it's very difficult to find out Fourier transform if you start from basic concept or forward Fourier transform equation. Rather, we'll use inverse Fourier transform to get the spectral of these signals. So what we'll do, we'll use inverse Fourier transform. We'll try to consider if del of omega is one spectral, then what is the signal corresponding time domain signal that we wish to find out. So spectral is del of omega. I want to find out its corresponding time domain signal. So inverse Fourier transform of del of omega is defined as 1 upon 2 pi integration minus infinity to plus infinity del of omega e to the power j omega t d omega. Okay, now again we'll use the same concept. If any function gt is multiplied with del t, we'll get again del t, but here we'll multiply with g of 0. Same thing we'll do. So this is your del function. So here we'll put omega equal to 0. So e to the power 0 equals to 1. Thus, so this is becoming only del of omega d omega, and its integral, you know, it is equals to 1 because it is unit impulse. So this value is 1. So thus it is 1 upon 2 pi only. So we have got that del of omega is the inverse or is the Fourier transform of 1 upon 2 pi. Means inverse Fourier transform of del of omega we have got 1 upon 2 pi. So in other words, I can say 1 upon 2 pi is the time domain signal. Its Fourier transform is del of omega. So if I multiply both sides 2 pi, then left side will become 1 and right side will become 2 pi del omega. Thus, for 1, the Fourier transform is 2 pi times del omega. This is one important result we need to remember. Okay. So this is the shape. The signal is constant in time domain, DC. Its spectral is impulse. Okay, and function exact value is 2 pi times del omega. So whenever you will get some DC or pure AC, pure sinusoidal signals, every time you will get del function. So you should remember this concept. But if signal is time limited, then you won't get any del function. But if signal is time unlimited, it's a periodic or a DC, then you will get a del function. Okay, that thing we have discussed in detail in one lectures. You will get the link of those videos in the description. You can follow that one. Now I'll consider one signal x of t equals to e to the power j omega naught t. So this is one complex signal with frequency omega naught, and you know e to the power j theta can consider as cos theta plus j sin theta. So it is having two component, cos omega naught t plus j sin omega naught t. And you know cos omega naught t, the frequency is omega naught. Again sin omega naught t, its frequency is also omega naught. Okay, thus this signal is also having a frequency omega naught. We want to understand its spectral. Again we'll use inverse Fourier transform. We'll try to compute the inverse Fourier transform of this function del omega minus omega naught. So inverse transform of this one del omega minus omega naught multiplied with e to the power j omega t. Then you need to integrate, and we should take one scaling factor 1 upon 2 pi. Right. Now again we'll use the same concept. If any function g of omega del omega minus omega naught is multiplied, you see this del function will exist at omega equal to g omega naught only. Otherwise it is 0. So I can replace omega by omega naught in this function. So that will give you certain weightage on this impulse, but nature will remain impulse located at omega equal to omega naught. So g omega times del omega minus omega naught we can rewrite as g of omega naught times del omega minus omega naught. That we will do here. So this is the function multiplied with this function. So here this omega is replaced by omega naught. Now as omega is replaced by omega naught, this is independent of continuous variable omega. I can take this one outside. Okay. Now I'll integrate only this function del omega minus omega naught d omega, and this integral is 1 because it is unit impulse located at omega equal to omega naught, but range is minus infinity to plus infinity, so it will include this signal's position. Thus the area is 1. So as this area is 1, now we'll get this is 1 upon 2 pi e to the power j omega naught t. So it shows that time domain signal is this one, 1 upon 2 pi e to the power j omega naught t. This time domain signal, its Fourier transform is del omega minus omega naught. Now again, if I multiply both sides by 2 pi, we'll get e to the power j omega naught t, and right side the spectral is 2 pi times del omega minus omega naught t. So this complex signal, periodic signal, it is having a single frequency at omega equal to omega naught. So here you are having one impulse. So spectral is 2 pi times del omega minus omega naught. This is one-sided spectral, remember. So this exponential signal e to the power j omega naught t, it is having here only. And if I consider e to the power minus j omega naught t, then we'll get one impulse at minus omega naught. Okay. So that will come later. Now I'll use few properties. I'll discuss all the properties in detail a little bit, but we'll try to avoid the proofs of those properties. I have discussed the proofs of those properties in detail in my lectures. So link for those videos will be given in description. Okay, you can follow those things if you want to go understand in more detailed way. Okay, so we'll discuss all the properties which are useful to solve the problems from Fourier transforms. Okay, so first property is the linearity. It says that if I consider one signal x1t, its Fourier transform is capital X1 j omega. Another signal x2t, its corresponding Fourier transform is capital X2 j omega. Now if I consider one linear combination a times x1t plus b times x2t, this linear combination, then its Fourier transform will be again similar linear combination of their spectrals. Means same coefficient a is here. Now its spectral is capital X1 j omega, and this is b times x2 j omega. If I can combine these two, I'll get overall spectrals. So I can consider one composite signal taking linear combination of two or more signals, and we can use linearity. We can find the Fourier transform of this composite signal very easily, taking those linear combinations of their spectrals as well. So this is very useful. Second property is time shifting. If x of t is delayed by another amount t naught second, so x of t minus t naught, that time Fourier transform will become. So you see, one signal is shifted right side or left side, whatever it is, but its shape will remain same. So its frequency content will remain same. Okay, so its pattern of this spectral will remain same, but this time delay corresponding to one phase delay, that is denoted by e to the power minus j omega t naught multiplied with x of j omega. So this is the implication. X of t minus t naught, one time delayed signal, will give you one phase delay, that is multiplied e to the power j omega naught t, omega t naught is multiplied with x of j omega, right? Now we'll consider third property, that is the time scaling property. So x of at, its Fourier transform is 1 upon mod a capital X of j omega upon a. Okay, so depending on a, you will get one compression or expansion of the signals. If a is more than 1, the signal is compressed, and if a less than 1, then signal is expanded. Okay, so you can understand that if signal is expanded in time domain, means it is changing slowly, thus frequency content will be low. Meaning is that it will be opposite of this one. Again, if signal is compressed in time domain, meaning is that it is repeating or it is changing more frequently, meaning frequency is more. Thus, if signal is expanded in time domain, the spectral is compressed in frequency domain, and vice versa. Okay, that is given by this one. So this is the scaling factor 1 upon mod a. So x of j omega upon a. So a can take any value, including 1 and negative as well. Okay. Now next property I'll consider, that is called time reversal, the special property of time scaling. If I put a equal to -1, then you will see this is becoming 1 and it is your x of minus j omega. So if I consider one time reversal, mean time folding, so positive part is becoming negative, negative part is becoming positive of that kind of signal, then shape is remaining same. Just only thing is that frequency, now positive frequency will become now negative frequency will become now positive frequency. That's all. Okay. So this is the implication. So what pattern will remain same. So it is also useful. Next one is conjugate property. So if I take conjugate of this signal xt, we'll assume that xt could be complex. Okay. So x star t, star is for conjugation, conjugate x star t, the conjugate of xt. And if I take Fourier transform, then we'll get capital X star of minus j omega. And these proofs are very simple. I have discussed this thing in detail in my previous lectures. Please go through those videos if you have any doubt. So here our focus is to understand all the properties in briefly so that we can solve the problems. Now using these 5 properties, we can have these following observations. So that I will discuss a little bit. The first observation is, if xt is real signal, right, then the x star t, x star of j omega will become capital X of minus j omega. Meaning is that its negative frequency is the conjugate of positive side frequency. Meaning the spectral is having conjugate symmetry property. Right side and negative side, left side, these two frequencies, they are conjugate to each others. That is the meaning of this one, right? So now how to prove these things? Very simple one. X of t, its Fourier transform is capital X of j omega. And if you take the conjugate on both sides, we can easily show that x star t using conjugate property, it will be capital X star of minus j omega. Okay, this is from conjugate property, and this is by definition of Fourier transform. Now if I use these two, and if I now consider that xt is a real signal, as xt is real signal, so if you take conjugate, it will remain same because signal is real. So conjugate of real is again same signal. So thus x star t is again xt. Thus if I take Fourier transform both sides, left hand side is x star of minus j omega is Fourier transform, and its Fourier transform is capital X of j omega. Now if I both sides replace omega by minus omega, so here it will become capital X star of j omega, and here it is becoming capital X of minus j omega, right? Thus you see it is proved for negative frequency it is having conjugate shape. Next one, if xt is real and again even signal further, right, then this x star j omega will be first of all x of minus j omega because it is real, and again it will become x of j omega, means this will show you that it is even again. X of negative equals to x of positive means it's even function, meaning the spectral is real and even. And we can easily prove this one. X of t is even signal, we have assumed. So x of minus t equals to x of t. So taking Fourier transform both sides. Now the left hand side, its Fourier transform will be a capital X of minus j omega, because its time reversal property we have considered. The if I consider x of minus t, its Fourier transform will be capital X of minus j omega using time reversal property. Now its Fourier transform is x of j omega. So x of minus j omega equals to x of j omega. It's implied that the function capital X is even, say even symmetry, right? Now as it was real, obviously it will show conjugate property, right? So meaning is this one, this capital X star of j omega, already we have proved that it is capital X of minus j omega, it is for xt is real. And x of minus j omega, already you have got capital X of j omega. So meaning is x capital X star of j omega is same as capital X of j omega. Try to understand. This is important. I have got one function capital X, its conjugate is again same. What is the meaning? Meaning is that that function is real. If it is complex, obviously conjugate will be different. Okay, so as we are getting the same function after taking conjugate, thus the signal is obviously real. And already you have seen that this function is even. Thus, when xt is real and even, its factorial is also real and even. In the same way, we can prove that if it is real and odd, it will be imaginary and odd. Why? Because if xt is odd, x of minus t, I can write minus sine x of t. So from here, if I take Fourier transform, this is your x of minus j omega, and this is your x of j omega with minus sign. It clearly shows its negative value of x, capital X, is minus of positive value, means it's an odd function. Okay. Again, as x of t is real, we'll start with capital X star j omega equals to capital X of minus j omega, and this one I can replace by minus x of j omega. Okay. And so capital X star of j omega equals to minus of x of j omega. One function, its conjugate is just negative. It is possible if and only if the function is purely imaginary, like capital X equals to j times of b kind of thing. Then x star will be minus jb. Thus, x of j omega is purely imaginary, no real part, and it is also a odd function. So if xt is real and odd, its spectral is imaginary and odd. Now we will find the Fourier transform of these following signals using the properties, these few properties, only these five properties, using the five properties we have discussed right now. Using those things, we can find the Fourier transform of these signals. These are all important signals. So this lecture is going to be lengthy, but once you can go through this video fully, I hope you will be able to solve any problems from Fourier transform. So my advice is, please go through this video carefully, try to understand everything. Okay, at the end you will see that this part will become very simple. Okay, let us start. So first signal we'll consider this one, e to the power minus a mod t. So its Fourier transform, we want to show that it is 2a upon a square plus omega square. So e to the power minus a mod t. We can write this as, for right side t more than 0, this is e to the power minus at. To indicate right side, we'll put ut, because ut is one function. To indicate right side only, left side is 0. So this is one part for right side t more than 0, and left side mod t is replaced by minus t, thus minus minus is plus, e to the power plus at and u of minus t to indicate it is a negative side part. So combination of these two, right side part and left side part, total signal e to the power minus a times mod t. So as it is a combination of these two, we can use linearity property. Already we have got the Fourier transform of e to the power minus at, and we can use other properties to find these things. Let us see. So Fourier transform of e to the power minus a mod t. Its Fourier transform, already you have seen that it is 1 upon a plus j omega. Remember, we will be using the result of previous signals, means spectral of your signals directly. You need to remember the spectral of those signals that already we have discussed. Okay, again we will try to remember this signal as well to simplify or to solve the other problems. So e to the power minus a mod t. So this is the first part, this is the second part, and its Fourier transform we have seen it is 1 upon a plus j omega. Now this one, you see, it is nothing but replacement of t by minus t. So if I replace t by minus t here, it will become e to the power plus a t. It is becoming u of minus t. So this signal is time inversion or reversal of this one. So for time reversal property, if I use, then omega should be replaced by minus omega. Thus this function there, or this omega should be replaced by minus omega. So I have replaced by minus sign here. So this is 1 upon a minus j omega. Now if you combine these two, then you will get 2a upon a square plus omega square, because product of these two, a plus jb, jw, and this is a minus j omega. If you combine these two, multiply these two, you will get a square minus j square omega square, and j square equals to minus 1. Thus you will get plus sign here, and numerator j omega minus j omega will cancel. You will get 2a. Right. Now we'll consider one signal. Here, this combination here is minus sign. This is e to the power minus at ut. It is e to the power plus at u of minus t. But if I take minus sign here, then this composite signal, its Fourier transform, if I compute, I'll get this one. And that is very easy, because if I take Fourier transform for the both of these two parts, for this one it is 1 upon a plus j omega. For this one it is a minus j omega, but here it is minus sign. So here a cancel out, so you'll get numerator minus 2j omega and denominator a square plus omega squared. And signal, if we consider this one, this composite signal, this is exponentially decaying signal. Starting from 1, right side will decay to 0, and this one including minus sign, because of minus sign it will start from minus 1 here and it will decay to 0 here again. Okay, this is your minus e to the power plus at u of minus t, and this curve is e to the power minus at u of t. So the combination of these two is total signal. Right. Now we used to find out the Fourier transform of sine or signum function, signum t, and it is defined, the signum t is defined as, for t more than 0 it is plus 1, and t less than 0 it is minus 1, more than 0 plus 1, less than 0 minus 1, at t equal to 0, to avoid discontinuity we may consider it 0. Okay, so this is a signal. We need to find out Fourier transform of this signal. This is commonly used. Okay, we'll be using this function several times, like in Hilbert transform or something other places. We'll be using these things, right? Okay, now we'll start from that previous example. This signal x of t e to the power minus at ut minus u e to the power minus at u of minus t, and its Fourier transform we have got minus 2 j omega upon square plus omega square. Now if I consider a tends to 0, if I consider a limit a tends to 0, then this function is not decreasing at all. It will remain at 1. Okay, because e to the power 0 equals to 1, so right side is ut, and left side minus sign e to the power 0 is 1 again, u of minus t means this one. So right side plus 1 and left side minus 1 means you will get simply signum function, right? So this function actually we can obtain from this above one, considering a tends to 0. So if I put a tends to 0 in the Fourier transform, so its Fourier transform will become this one, because I need to replace a equals to 0 here. So a is 0, it is minus j omega upon omega square. So if you simplify, it will become 2 upon j omega, because I can consider it is j square equal to minus 1, 1 j will cancel out, and minus minus cancel out, you will get 2 upon j omega. So this is a useful result. Sin t, or signum t, its Fourier transform is 2 upon j omega. Next, we will consider the step signal. So you see the sequence from where we have started and what we are doing. Okay, you should follow this sequence. Then only you will be getting all the results in a systematic manner. Okay, now we'll compute the Fourier transform of step signal. And we can show that its vector will be 1 upon j omega plus pi times del of omega. Because ut now I can write as half of signum t. It should be signum, sgn. Okay, remember, signum t plus half. So this signum, so what is this half of signum t? Means this is your signum t plus 1 and minus 1. Now it's half percent, means right side is half, left side is minus half. Now with this, if I add half, so left side is minus half and plus half, it will become 0. So left side is becoming 0. And right side plus half and again plus half, it will make plus 1. Okay, so left side is minus, sorry, 0, and right side is plus 1. This is nothing but ut. That is actually combination of these two. One is half of signum t plus half, right? Now I can take Fourier transform. So Fourier transform ut. Now Fourier transform of this one, already we have got the Fourier transform of this one. It is 2 upon j omega. And we know the Fourier transform of this one, dc. For dc, Fourier transform is 2 pi del of omega. Okay, and then we can take linearity combination. Okay, so its weightage is half. So half times this, its Fourier transform is 2 upon j omega, plus this is half times the Fourier transform of 1 is 2 pi del omega, 2 pi del omega here. So this will give you the Fourier transform of ut. So if you simplify, this 2 and 2 will cancel. It is 1 upon j omega. This 2 and cancel. This pi times del omega. Okay. So this 1 upon j omega plus second term pi del omega. Don't forget to consider these things, because it indicates that the signal is having one DC component. So half is the DC component. Because of this, you are getting this pi del omega. I told you that whenever signal contains some DC or pure sine wave or cos wave or periodic signal, then you will get certain del function in spectral. Okay, so del function at omega equal to 0 indicate it's having one DC, and other than 0 means it is having that kind of frequency, periodic frequency. Okay, now if I consider cos omega naught t, so this periodic signal, so already I've said that for periodic signal we should get del function, and if I consider cos omega naught t, its Fourier transform will be pi times del omega minus omega naught plus pi times del omega plus omega naught. One located at omega equal to omega naught, other del is located at omega equals to minus omega naught. Now it is very easy to prove, because cos omega naught t I can express in this form, e to the power j theta plus e to the power minus j theta by 2. So here it is half of e to the power j omega naught t plus half of e to the power minus j omega naught t. So the Fourier transform of this one is very simple. This is the, I can use linearity as well as time reversal. And one more thing, e to the power j omega naught t, its Fourier transform already we have computed. It is 2 pi del omega minus omega naught. Therefore, using time inversion or time reversal, if I put t equal to minus t, I'll get t to the power minus j omega naught t. Its Fourier transform will be omega should be replaced by minus omega. Okay, so here you'll get del minus omega naught. That I can consider del omega plus omega naught, because del of minus omega and del of plus omega actually it is same. Okay, so now you see this is the weightage half, and for this one it is 2 pi del omega minus omega naught. This is plus sign, this is half. This one is spectral is 2 pi del omega plus omega naught. So 2 will cancel out everywhere. It is pi del omega minus omega naught plus pi del omega plus omega naught. So if I show it in figure, so I'll have one impulse here at omega equal to omega naught, one more impulse at minus omega naught, that is here, and this value is pi times del omega minus omega naught. This is your pi times del omega plus omega naught. So see the difference between simple exponential signal, complex e to the power j omega naught t. In e to the power j omega naught t, I had only one impulse located at omega naught. That time value was 2 pi del omega minus omega naught. Okay, right. Similarly, we can go for sine omega naught t, and its value will be minus j pi del omega minus omega naught plus j pi del omega plus omega naught, because sine omega naught t I can replace by e to the power j theta minus e to the power minus j theta by 2j. So I'll have here it is minus sine, here it is j. Because of this I am getting one j factor here. 1 upon j is minus j, and here it will become plus j. That's all. So this one at omega naught, I'll have one impulse minus j pi del omega plus omega minus omega naught. Here it is one impulse j pi del omega plus omega naught. Right. Now we'll discuss one new property, useful property, that is differentiation in time domain. So if I take derivative in time domain, dx dt, and its Fourier transform will be j omega times x of j omega. It's very simple. First you can start with x of t and its Fourier transform. So better that you can go for inverse Fourier transform. Then take derivative on both sides, you will get the result. Here I'll show you one example where we can use this differentiation property. Consider this gate signal or rectangular signal. Already we have computed this pi of small t upon capital T. The width is capital T and amplitude is 1. Okay. For this signal, I can find out the Fourier transform using this property. Okay. So if this is a signal, now if I take derivative dx dt, so derivative means the slope. So here there is no slope, it is not changing. Slope is 0. So here certain change is there. At minus t by 2, there is certain change 0 to 1. So slope is infinite. That imply that derivative is impulsive. Okay. So if I take derivative, here I will get one impulse. And it is positive impulse because it is increasing 0 to 1. So that I will consider del, and it is located at minus t by 2, thus del t plus t by 2. And here it is 0 because this value is constant, derivative is 0, slope is 0. And here there is certain change again, 1 to 0, thus you will have one impulse here downward, but it is downward because change is from 1 to 0, it's negative. So 0 minus 1 is negative. So thus here this one I will consider minus sign del t minus t by 2. So this is your derivative of this signal. Now I can take Fourier transform of this equation on both sides. Okay, so left side will be using this property j omega times x of j omega, and already we know the Fourier transform of this one del t. Fourier transform of del t is 1, but it is time shift. It's time advance t by 2, so there's a phase advance, it is for j omega t by 2, and its del t is 1, that I have not written. Similarly, it is time delay. For time delay, it is a phase delay, e to the power minus j omega t by 2, and spectral is 1. Okay, that I have used. Now I can find out x of j omega. So this j omega I can divide both sides. So it will be becoming e to the power j theta minus e to the theta by j omega. So now I can consider 2j here. So this will become sine part. So as I have considered 2 here, I need to multiply 2 here. So this is becoming 2 upon omega, and this is becoming sine omega capital T by 2. Right? So same thing I have obtained using differentiation property. You can notice that I have not used any integration. Just using the properties only, I can find out the Fourier transform of this kind of rectangular signal. Next one, convolution in time domain. So if I have one signal x1, its Fourier transform is capital X1 of j omega. Another signal x2, its Fourier transform is x2 of j omega. Then if I take convolution in time domain, x1t convolution x2t, that signal, its Fourier transform will be simply multiplication of their corresponding spectral, x1 of j omega times x2 of j omega. And proof is little bit difficult. I have discussed this thing in detail in one of my video, and link you will get in the description. Okay, so you can follow that proof if you want to go through. So this one is useful, especially in the system, LTI system. In LTI system, you know that if impulse response is given h of t, then for any signal xt, we can find out output yt. And that time output yt is nothing but convolution of input signal and its impulse response h of t. So xt and h of t. Thus, so if I take Fourier transform, its Fourier transform is capital X of omega, its Fourier transform is capital H of omega, then Fourier transform of output signal y of omega will be simply x of omega times h of omega. So we can find the spectral of output signal easily using this convolution property. One more example, that we can also find the Fourier transform of certain other signals. Suppose if I have one triangular signal like this, minus t to plus t, so from minus t it is growing to reach 1 at 0, then again it is decreasing, it is becoming 0 at capital T, then to remain 0. So this is your triangular signal, and we are interested to find out the Fourier transform of this triangular signal. In a similar way, we can find out. You can use differentiation property. If you take derivative, then left side will become one window function, right side will become another window function here, but it's negative slope, here it is positive slope. Then you can use the property of or the result of window signal and the property of derivative. There, in that way you can solve it. Another way, you can also solve this thing using convolution property. How? Because this triangle signal we can obtain if I take convolution between two rectangular signals or two gate signals of phi t upon capital T. So if I consider phi t upon capital T convolution with phi again t upon capital T, you will get this kind of triangular signal, but to get amplitude 1, I need to divide 1 upon capital T. Okay, so this xt is nothing but convolution of these two gate signal multiplied by 1 upon T. Okay, that you can prove it. So I have discussed convolution in detail in one of lecture, you can go through. So this x of j omega, by simply using this property, the product. Okay, so this is one scaling factor 1 upon t is fine. Its value is 2 upon omega sine omega naught omega t by 2. Again its value is same, so I'll get a square of that one. So it is 1 upon t times 2 upon omega times sine omega t by 2, that's square. So you know that this is becoming sin function. So triangular signals, its spectral will become sin square. So this is very useful. So sin square function is the spectral we are getting sin square. It is for triangular signal in time domain. Okay, we'll use this property. We can use this property. Now multiplication in time domain. So if I have two signals x1 and x2t, if I multiply in time domain, I will get the conversion in spectral domain. But scaling factor will be 1 upon 2 pi. So that I can check. Okay. Now modulation. Modulation property. So it is similar to this one. So this is x of t. This is your cos omega naught t. So if I consider this above one also, I can do that one. Okay, because I can take convolution of these two. Because omega naught t Fourier transform we have found out. Okay, it's a pi del omega minus omega naught and plus pi del omega plus omega naught. Then you can take convolutions. Okay, so then you will get simply, so this pi will cancel out, is half will be there, half x of j omega minus omega naught and half x j omega plus omega naught. It simply implies that if I know the spectral of x of t, then if I multiply this cos x of omega t with cos omega naught t, then spectral is shifted to right side by at omega naught. Again, spectral is also shifted left side by omega equal to minus omega naught. So this modulation is called double side surface carrier. So this is useful in communication. So you will understand this thing in detail in communication. Here I will not discuss, but this is a basic concept. You will get double side. Then next property is area under x of t. It is also useful. Okay, that thing we can find out. So integration of x of t dt, this area under xt will be simply the 0 capital X of 0, the value at omega equal to 0, x of omega. Okay, so that is very easy to understand because the capital X of j omega, its Fourier transform is given by integration of x of t to the power minus j omega t dt. Just put omega equal to 0 on both sides. Right side, this part will become 1. Thus, this is your integration of x of t dt, and left side is x of 0. That's all. But this is useful because sometimes one integration is not easy to compute, but it's Fourier, if I know that it's Fourier transform, we can easily find out its value at origin. So that will give you the integral sign. Okay, so I'll discuss this property. Then area under x of j omega, the opposite one. So integration x of j omega d omega entire range, it will give you 2 pi times x of 0, because from here only we can, so inverse Fourier transform, x of t equals to 1 upon 2 pi integration x of j omega t power minus j omega t d omega. So here we can put t equal to 0 on both sides. So if I put t equal to 0, this will become 1 and it will 0, it's x of 0. And if I multiply both sides 2 pi, you will see this is your integral. This integral is 2 pi times x of 0. Okay. Next, integration in time domain. If I integrate this signal x of t in time domain, okay, means minus infinity to x of tau d tau. If I consider this is one signal, then its Fourier transform will be capital X of j omega upon j omega plus pi x of 0 del omega. Right? This thing we can prove it considering that this integral minus infinity to x of tau d tau I can consider as the convolution of xt with ut, because ut is this convolution, you know that x of tau, u of t minus tau and that integral, and u of t minus tau is 1 within minus infinity to t only. Okay, thus the range will be minus infinity to t, and that u of t minus tau is even 1, and so it will be simply x of tau d tau. Okay, so This integral I can replace by convolution of xt and ut. Now I can take Fourier transform both sides. So this its Fourier transform will be then Fourier transform of this one, and we can take product. We can use convolution property. So its Fourier transform is x of j omega, and Fourier transform of ut already we have computed 1 upon j omega plus pi del omega. So if I expand it, one term will be x of j omega upon j omega, and second one is x of j omega times pi del omega, and as is the product of these two, and it will exist at omega to 0, thus I can write x of 0 only. So pi x of 0 del omega, it's sufficient, right? So this part will be there if x of 0 is non-zero. Meaning is that x of 0 imply DC value, omega equal to 0. So if signal is having one DC value, then only this integration will have one DC component. Otherwise, this part is absent. You can ignore, right? Now differentiation in frequency domain. So if I multiply jt with xt, and then if I take Fourier transform, you will get minus dx j omega d omega. That also you can prove it easily. So you can start with the Fourier transform definition, then take derivative on both sides with respect to omega, and you can then compare, you will get this one result. I have discussed this thing in detail in one video. You can go through. Duality. This is another important property. If x of t, its Fourier transform is x of j omega, then if I take this shape, capital X, this shape in time domain, means capital X of t, then Fourier transform will be 2 pi times of this shape small x of, but here it should be replaced by minus j omega. Okay, that's all. So this is useful. So I'll show you one example. So this duality property, suppose this is one rectangular signal. Already for this get signal, we have computed Fourier transform. It is a sinc function, 2 upon omega sine omega t by 2. So if I use duality property, if I take this shape in time domain, the sinc function in time domain, like this shape in time domain, it's t. So I replace omega by t. So I'll get 2 upon t sine t 2 omega naught by 2. This is the signal. Okay, and here I have considered capital T is replaced by 2 omega naught. Suppose if I consider, so this signal, so if you simplify and then if you take duality property, so you should get this shape in this side, Fourier transform, and with time inversion or frequency inversion, this shape. And as it is even function, it will shape will remain same. But you see here t I have considered 2 omega naught. So here I got 2 omega naught by 2, 2 cancel out. So it is becoming omega naught, and this is becoming minus omega naught. At now, so this 2 pi times, so its amplitude will become 2 pi. Right? Now if I divide both sides by 2 pi, then this amplitude will become 1. I divide by 2 pi here, 2 cancel out, and here this 2 cancel out. So this one I can simplify as sine omega naught t upon pi t. So this is one well-known form. Sine omega naught t upon pi t, its Fourier transform is this gate function amplitude 1, and it will continue up to omega naught and minus omega naught. Right? This sine omega naught t upon pi t, its Fourier transform is pi omega upon 2 omega naught. This window is 2 omega naught, but center point is omega. So you see, if I have only sine omega naught t, its Fourier transform, we will get one impulse at omega naught and another impulse at plus minus omega naught. But whenever I will multiply with this with 1 upon pi t, its spectral is continuous from 0 to omega naught right side and 0 to minus omega naught on left side with magnitude 1. This is very useful, especially to design filters. So you'll see this spectral is close to ideal low pass filter, So if I say omega naught is the cutoff frequency, then this is one low pass filter. So ideal low pass filter, its impulse response should be sine omega naught t upon pi t, right? Next one is Parseval's identity. This is one useful. Using Parseval identity, we can relate the energy of the signal in time domain g squared t dt. If I consider gt is a real signal, otherwise you should consider again absolute value of gt that squared. Okay, so that total energy of a signal I can compute, and that energy of signal is same as this expression 1 upon 2 pi integration absolute value of g of omega that squared d omega. Okay, so this is your spectral density, I can say g omega, because if you integrate these things you will get again energy, so it is energy spectral density, right? So this is also useful. We'll use these things. Now I'll consider few problems on Fourier transform. Those problems will solve using those properties only. You see, these are beautiful properties, these beautiful problems, and I hope you'll be able to solve these things. We'll discuss in detail. So this lecture is going to be lengthy, but if you can go through till the end, obviously you will learn lots of things. You learn how to solve the complicated problems using these properties, all the properties. These 14 properties we have discussed with Parseval's, and also one Parseval's relations I have discussed. Using this, we can solve the problems. First problem is this one. Can we find Fourier transform of x of j omega, Fourier transform x of j omega of the signal x of t, which is t upon 1 plus t square, that's square. So this is the signal. Can you find Fourier transform? Okay. So you see this one. These are the choices given. Now how to compute the Fourier transform of this signal? This is a very interesting problem. Now where you have got this form 1 plus t squared. Okay. Can you recall these things? So you see we have considered one signal e to the power minus a mod tau, and its Fourier transform was 2a upon a square plus omega squared. So this square form I can get in spectral. So e to the power minus at, but here it is 1, so I will consider a equal to 1 here. So e to the power minus a mod tau mod t is Fourier transform is 2 upon 1 plus omega square, because of this. From here we will start. Okay. Now first I'll use duality property, because I want to get this safe in time domain first. Okay. So if I use one signal gt, which is 2 upon 1 plus t square, omega is reduced by t square, okay, then using duality, this shape you will get in frequency domain with scaling factor 2 pi times e to the power, but this t should be replaced by minus omega. So minus absolute value of minus omega. Okay. So don't think that you replace by t by j omega. No, not like that. T should be replaced by minus omega. That is the same. Okay. So 2 pi e to the power minus absolute of minus of j omega minus omega, and this is again mod of omega, the same thing. So it is 2 pi times e to the power minus mod of omega. Suppose this is your capital G of omega. Okay. So far we have got this one, but we need to get this thing. So how to get this safe from here? Now I want to get squared, this denominator square. So it is 1 upon x. So if I take derivative of 1 upon x, I will get 1 upon x square. Okay. So that concept we will use. So now I will use differentiation property. So if I consider one signal which is derivative of this signal, so xt is dg dt. So by derivative property, it will be j omega into g of omega. Now you see that what is this function xt. So this derivative will be 2 is there. So its derivative minus sign 1 upon 1 plus t squared, that square, and derivative of then t square is 2t. So this is your total derivative. Okay. And right side is j omega, and g omega now we can replace. It is 2 pi e to the power minus mod omega. Okay. Now this minus 4 is not there. It's 2 into 2 4 minus sign. So I can divide both sides by minus 4. So it is minus 4t 1 upon t square whole square. That's Fourier transform. We have got this one. So therefore t upon 1 plus t to the square, I'll divide by minus 4 both sides. So if I simplify it, so 2 cancel out, and this is your j and j, 1 cancel out. So minus sign I can write by j square. So 1 j will cancel out. I'll get j here. So it's pi upon 2j omega e to the power minus mod of omega. Okay. So you see, this one is the correct answer. So this is important problem. Very nice problem. Next one. Now look at this problem. So it's a connected problem. So it says that one impulse response h of t of a system, linear system, is given exponential e to the power exponential of minus 2t ut. This is your h of t. Now first we need to find out h of j omega. This is the first problem. And second problem is, if I apply one signal x of t equals 2 cos of 2t, then what is the corresponding output? Okay, so these two problems we want to discuss. So first problem we'll consider here. That is very easy, because this is a system given h of t, xt and yt, and ht is given here e to the power minus 2t ut. Already we have computed the Fourier transform of this one. So h of j omega is simply 1 upon a plus j omega. A is in this case 2, so 2 plus j omega. That's all. Okay. Now second one is this one. Now if I apply one signal x of t equals 2 cos 2t, then what will be the output? So this is system. This is your impulse response. This is your frequency response. I'll call it h of j omega as frequency response. So we know the magnitude plot and phase plot. Magnitude is 1 upon 4 plus omega squared square root, and phi is minus tan inverse omega by 2. Right? Now if I apply xt equals to a cos omega naught t, then we can show that the output would be similar to again cos. The cos will remain cos. Okay, and frequency also remains same, omega naught. So only thing is that amplitude is modified by this amplitude. It's multiplied a into am of omega naught, and one phase is added. This phase will be added with this cos. So output will be a into am of omega naught times cos into omega naught t plus phi of omega naught. Okay, so this is the result. We can discuss this thing in detail in one video. Okay, right now we'll use this form. So for this one, a equals to 2 and omega naught equals to also 2 radian per second. So if I replace this one here, this omega here, and so I'll get am of omega naught and phi of omega naught both. So am of omega naught will be 1 upon 4 plus omega square 2 square. So it will be 2 root 2, 1 upon 2 root 2. And phi of omega naught is minus tan inverse 2 by 2 is minus pi by 4, means minus 2.54 pi, 2.5 pi. Okay, so if I combine these two, what will get? A into a is in this case your signal 2, so 2 into 1 upon 2, 2 will cancel out. Okay, so 2 into 1, this is multiplied with amplitude, and this with cos 2t, this phase is added. So you see it is becoming 1 upon square root 2 cos 2t minus 0.255, right? So this one is the result. So this is nothing but answer D. Okay. Next problem. So can you find the integral of this one? 12 cos 2 pi t times sine 4 pi t upon 4 pi t. Okay. This is very difficult problem. It looks like difficult, but it's not so difficult. We can solve it. Okay, using these properties only. So let us start. So for this, we'll use these properties. First, we'll try to use the integral of xt dt, that is nothing but x of 0. So integration in time domain. Okay, so means area under the time domain signal xt will be x of 0, capital X of 0 only. That property. Next, modulation property. I can use xt cos omega naught t will be half x omega minus omega naught, half x omega plus omega. Remember that sometimes I'll remove the j. J indicates that it may be complex. That's all. But it's a function of omega. That is the main thing. So you know that x of t, its Fourier transform, I can write x of j omega or x of simply omega. We can discard omega. Right. Last property, this one, sine omega naught t upon pi t. This is not property, it's one result. This function, its Fourier transform we have got, it's a rectangular function, inspector. So now I'll consider this integral. Now this is the 3 and this is the integral. Okay, we need to compute. Now this is the arrangement. You see this 4 I have considered here only, so it is 3. So this part is becoming sine 4 pi t upon pi t. This kind of form. Here omega naught equals to 4 pi. Right? So this is one function. And with this cos 2 pi t is multiplied. So if I consider this is your xt, then xt into cos omega naught t, this form is factorial we can get using modulation property. So we'll use all those things. So in our case, the x is this one, sine 4 pi t upon pi t. And then we'll multiply this cos omega naught t. I'll get the spectral. And this spectral from that spectral. So then if we can integrate this signal, that is nothing but we need to find out the magnitude at omega equal to 0. That's all. This is one way. Okay. So I can consider that this is the first approach to use this modulation concept. Now, so xt is sine 4 pi t upon pi t. Its Fourier transform is this one. It's flat 1 up to 4 pi and minus 5. Okay. Now, okay, I write here. Then, if I multiply xt with cos of 2 pi t, so you know that whenever we will multiply with cos omega naught t, the spectral is shifted around omega naught and minus omega naught, both. Okay, so this spectral will be shifted right side one time, again left side, okay, by omega naught. In this case, omega naught is 2 pi. So 2 pi shift. So the minus 4 pi is shifted by 2 pi right side, then it will become minus 4 pi plus 2 pi is minus 2 pi. Okay, it is coming here. And this 4 pi will come to 6 pi, 4 pi plus 2 pi. So this one, this curve is for half these things shifted right side. And then magnitude should be half of this one. So this part, half x of omega minus omega naught. Similarly, I'll get this one. This is half omega x of omega plus omega naught. So then I need to add these two. So you see this region minus pi 2 pi 2 plus 2 pi, both the function they are overlapped and both the values is half. So if you add these two, half plus half, it will become 1. And other side, this region is only this is existing, and this region, this will exist, so it will remain there. So the resulting signal, I'll call it GT, and its omega is capital G of omega. It will look like this, because here to here it will remain half, it is remain half, but here it is becoming half plus half is 1. Okay, so I have got this one GT, that function. I need to compute, remember, I need to compute this one. This is your GT now, because this is your xt, this is your cos omega t, this is your GT. So I need to integrate this thing, GT integration. So 3 times of this one is nothing but 3 times of integration of GT, that I can consider using property, that area under time domain signal will be capital G of W, this one. So it is 3 times of capital G of 0, and from here capital G of 0, I can see that its value is 1. So that I replace this 1. So 3 into 1 is 3. Okay, so answer is 3. So this is one way. The second method, no need to use this convolution property. Without convolution also we can find out. Okay, that is possible. So for that, what you will do? So I'll start with this thing again. This is your xt signal, sine omega t by pi t. We know the spectral is this one. Now this one, 12 cos 2 pi t sine 4 pi t upon 4 pi t. So that we can write as, this is, I can write that 2 I can take out in this one, so it is outside 6, and 4 I can take outside, so it is 6 upon 4. This is 2 sine a cos b form, sine 4 pi t into cos 2 pi t dt upon pi t. Now this, as it is sine a cos b form, 2 sine a cos b, I can replace sine of a plus b plus sine of a minus b, like this. So this one is becoming sine of 6 pi t, and again minus sine of 4 minus 2 is 2, sine of 2 pi t upon pi t. Now we can distribute this thing, no? That we can separate this thing. See, it is 3 by 2 integral sine 6 pi t upon pi t dt. Again 3 by 2 sine of 2 pi t upon dt. Now this is one signal, its integral. And this signal is this signal. Its spectral will be up to omega naught. Omega naught is 6 pi. Okay. So you see, what is the spectral? Its spectral will be 1 up to 6 pi and minus 6 pi. And for this one, its spectral will be 1 within 2 pi to minus 2 pi. So the area under this time domain signal will be the value at 0. At 0 it is 1, it's also 1. So it is 3 by 2 into 1, again 3 by 2 into 1. So total value is again 3. Okay. So in this way also we can solve this problem. Okay. So we'll consider next problem. This one function gt, integration minus infinity to plus infinity, g of t e to the power minus j omega t dt equals to omega e to the power minus 2 omega squared. Okay, this is one real valued omega, and if y of t is minus infinity g of tau d tau, then you need to find out the area under yt. Okay, this is the question. It's a beautiful question. So how to tackle these things? Now, already said that this is equal to given this one. So what is this? This is nothing but Fourier transform of gt. I can write it as g of omega. Okay. Then what is given? Yt. Yt is minus infinity g of tau d tau. It's an integrator. If I integrate this signal, then I'll get yt. So now I can use integration property. So what is y of omega? Y of omega will be g of omega upon j omega plus pi g of 0 del omega. Right? Now g of omega is already given. So at omega equal to 0, its value will be 0 because of 0. This is 0. 0 into something is 0. So g of 0 is 0. Thus this part will vanish, is 0, and this part will be replace this thing by omega times these things. So this omega cancel out. It is minus j e to the power minus 2 omega squared. So we have got y of omega. Next, we need to find out area under yt. And area under yt, this integral is nothing but y of capital Y of 0. So in this factorial, just put omega equal to 0. So it is minus j, and e to the power 0 is 1. So it is minus j. Okay, so answer is minus j, this one. It's very simple. If you can use all the properties in proper way, you will get the result very quickly. Otherwise, it's very, very difficult to solve. The next problem, this one. The value is, you need to calculate this value, minus infinity to infinity, sin square 5t dt. Right? So how to compute this one? It's very difficult, it's not easy. Sin square you need to integrate. So what to do? So sin x is defined as sine of pi x upon pi x, that notation I'll use. So sin of 5t, I'll consider sine of 5 pi t by 5 pi t. Right? Now, if I consider xt as sine omega naught t by pi t, we know the Fourier transform. Fourier transform is this window signal. Minus omega naught to plus omega naught, its spectral is 1. So in this case, I consider this, it's gt equals to sine 5 pi t upon 5 pi t. So obviously its spectral will be up to 5 pi and minus 5 pi, right? But as it is given 1 upon pi 5, so amplitude is 1 upon 5, because only sine of 5 pi t by pi t is these things, amplitude 1. So scaling factor is 1 upon 5. So its scaling factor is 1 upon 5. Right? Now, this signal, what I need to do? G squared t dt. Now I'll use Parseval sin dt. So minus infinity g squared t dt, energy of the signal, I can compute from spectral. I need to integrate one integration of mod of g of w squared d omega and scaling factor 1 upon 2 pi. Because it is much easier, because this spectral is very smooth, one rectangular window. So that integration we can compute it very easily. So what then? So this thing square of this one is nothing but this area then. So it's squared. You need to take square of this one, then area, obviously. So this scaling factor is 1 upon 2 pi, and it's squared. First 1 upon 5, that's square, 1 upon 25. Then width is 10 pi, minus 5 pi to plus 5 pi. So width into height. Height is 1 upon 5, that's square, means 5 square, and width is 10 pi. So you see, if you simplify it, so 5 cancel out, it is 5 cancel out. So 1 upon 5 is 0.2. It's a beautiful problem. Okay. So if you have enjoyed this video, you can like this video, and you can share this one with your friends or your other persons who can like this one as well. And if you have not subscribed this channel, you may subscribe it, because in future I'll be adding lots of similar videos, other videos, and that video could be useful to you as well again. Okay, so thanks for watching. We'll meet again.